Alright, I think we're good today. To keep going with the next part, we're doing FPU, which is the floating point unit. It's another version, so we have the ALU, the arithmetic logic unit, that does like arithmetic operations like adding, subtraction. Sometimes can do multiplication and division because, like, from what I read, multiplication is just addition, just a different form, and division is kind of like subtraction, but just a different form. I think some CPUs implement multiplication and division within the ALU itself. Some have extra stuff, and floating points can be done in the ALU. So we have to actually separate that and use the floating point unit. So it's gonna be extra work, and of course the ALU also does like logic ops like AND, OR, NAND, all that stuff. So yeah, first I think we should start with the decoder and start adding floating point to it. To be honest, I think that's a good start for it. Yeah, I think that's a pretty good start for it. So first I want to actually like understand what's going on. Floating point, like I read over floating point, I understand most of it, but just to recap and see the actual layout of bits, I need to actually see what's going on here. So let's see. So for example, we have something like the first instruction being, these are two simplest ones, so float load word essentially, I'm pretty sure, and float store word. These to be simple. So the actual layout is, so you have an immediate from, and this takes up 12 bits from 0 to 11. Not 0 to 11, sorry. It takes from 20 to 31. It just takes 12 bits. And we have rs1, as usual, 5 bits, so it seems pretty similar there. Instead of func3, we have something called a width. Width, okay, that makes sense. Well, not really, I need to look over it. RD, destination register, that's the same as usual, so 5. We have 5 right there. And the opcode. So the opcode is also the same. It's just 7 bits, 0 to 6. So 7 bits is the same as other instructions for risc-v. But the opcodes obviously differ between each instruction type. So we gotta make sure we actually do this right. Alright, so let's just try and implement it. So first starting, do we need to implement anything in our struct? So yes, we do. So how should I do this? Okay, so this takes in the instruction name, destination register, and an immediate value offset with the rs1, which, can we see if there's anything similar to that in here? So that's kind of like that's just similar to an S-type instruction, I'm pretty sure. Like here, yeah. So load word, destination register, the immediate of rs1. It's okay. So let me think. Right, so we could make it the same. I don't know how it would scale if we made it the same as that. I don't know. So it's kind of interesting though to make it the same, because the extension is different. The extension is f extension, so, but the actual instruction is like identical, literally identical to our regular load instruction in the way that it's formatted. So should we store it as a new value in our struct, or should we not? In our enum class, sorry, in our enum class, or not? Should we change the value? That's what I'm thinking. Because like floating point unit is separate. So let me actually ask Plug what's more scalable if it's fine. So okay, so realize that W and FSW are identical to the okay to store them as S-type instructions, or make a separate version? I mean, I don't think it matters too much for this part. I think we can just store it as an S-type instruction. I think it matters for the memory, since floating points are stored differently in memory than integers. You need like a different implementation to say. But let's just see. For decoding, it might be S, maybe. Difference mainly occurs when the interpreter let's see. My reasoning should be right here to store it as an S-type, but let's see. Alright, so there's a couple things to clarify. FOW is not S-type, it's I-type. Wait. Oh, sorry. Not S-type. I meant it's under a memory instruction. Yeah. So it'd be I-type / load, FW would be S-type, same bit layout. So it's fine to actually store it as the same. Things get interesting. Loads from memory, floating point register, non-integer register. So yeah. So realistically, it should be fine to make it separate, make it the same here, and just separate it out later. So okay. Let me go back here. So it's the same as these I-type instructions, these load instructions. Well, okay, so I actually distinguished load to be these ones with the func 7, just these shift left logical immediate stuff. Here is just I-type, so we're just gonna store it as I-type. And yeah, so let's make the switches now. So we don't need to change anything in instruction type, but we do need to change it in the actual instruction itself. We'll store it in loads. Okay, wait, let me see. Yeah, loads are okay. Wait. I think how I distinguished it was regular at types, shifts, and loads. So it's like distinguished because they're all separate. Okay, so we need to store it under loads, which will be load. Let's see. Yes. So for now, just keep that in there as 1. We'll add more as we go through. Okay, so then we have FSW, which will be stored in S-type. Okay, so I think it's all good now here. So now we distinguish separately. So what do we need to do now? So let's analyze. So we're gonna try and implement float load word, which is what I believe it is. Float load word. Okay, so for this instruction, our immediate will be the same, but instead of taking a function, we have a width instead. So we probably need to get make a new function, but it essentially acts like func3. So I'm kind of confused on how. Like, I know we can. Okay, so let me think. So alright, so the width. Let's just check it here, right? So yeah, the width. Okay, it's identical, but instead of font 3, it is okay, let's see. Let's try to understand. Okay, essentially, right, the width field is in FP is sort of occupied the same bit position as func3 bits. So your existing getfunc3 function extracts it correctly already. It's just interpreted differently semantically. With value, 32-bit float, same patterns. The only thing that distinguishes FLW from load word is encoding is the opcode. So you don't need a new extraction function. So yeah, I'm just gonna keep it func3, to be honest, because after all, it's just a naming convention in the spec. Okay, so I guess I understand now that if things change up slightly, but not to a significant degree, if it's like only an identifier, then it's fine. But if it's something that's actually significant, like a instruction changes or something, but then we have to change it. But in this case, it essentially acts the exact same as the bits for that. We can actually take a look. So if you go back to load word, just a regular load word, as you can see here, it's the same. Immediate 12 bits, rs1 5 bits, func3 instead of width 3 bits, but it's the same position. And then same here, it's just the opcode is separate. So let's see. Alright, so nothing needs to change here for this instruction specifically. But in our decoder, we need to add here our case. Under loads, right? Okay. We need to make a new case here, which will be case instruction float load word, and it will be FLW. Alright, so essentially that's good. I'll also do the case here for store word. I think it's store word is essentially store word. We'll look afterwards to see if it's similar to store, regular store word. But for now, we'll do the load instruction. So we have the FLW now in there, and we also need to change in here. Actually, implement the logic for it. I'm actually gonna have a video going out tomorrow or the day after for my progress so far before floating point unit. But yeah. Okay, let's see. We'll just do it here. Yeah. These are extensions, so I just want it to be at the end here. So you have an else if. Okay, so let's analyze the opcode. So the opcode is, that's gonna be like hex 137. So hex 7. So opcode's gonna be hex 7, and func3 is 2. 0x2, right? Did that get the same one? Yeah, 0x7 and 0x2. He wrote 0x07. I don't know why he gave the extra 0x. Oh, it's the same. It's the same. I don't know why he distinguished. Okay. Okay, so that's fine. Now, the way that it distinguishes the name. Let's change the name. So it's gonna be FLW. Sorry, no. This will be load instruction. No. Type. I got mixed up, sorry. This will be, okay. Yeah, so that's good. And the values I take in are just these values, which we already have. Yes. That essentially makes it good. That's good. Okay. Yeah, okay, so that's pretty good. Let's try and do store word now, since we basically have the knowledge of that. Okay, so actually before we get to that, let's actually do the rest. We did it here, right? So FSW. Let's try and analyze the bits for that. Alright, so for FSW, we have the immediate. The upper immediate here takes about 7 bits, I'm pretty sure, 7 bits. And then we have another immediate, which stores about 5 bits from 7 to 11. For these floating point instructions, but let's see. So in our store, it's okay. So the layout is the same, right? Essentially the same. Taking the register source 2 and then taking the value from register source 1 and putting it in there, right? Yeah, that's essentially the same. So we need to actually see the actual floating point, how it changes now. So let's go back. Let's go to load. Save word. Alright, let's see the regular here. It's the same. It's the same. Hey, what's up, Exo? How you doing, bro? So I did more of the map. I added a mushroom biome with the mushroom parkour leading to a mushroom house. Have to add props. Added tube teleporters, move the shop area on the side of the map. We did the UI to look more like a Roblox from Masterclass. Nice, man. You should send me some. You should send me a DM. I'll see those. If you have, I'll check them out. I'll check them out on stream right now if you send me them. I'd love to look at them. Seems like you've done some good work for today. Alright, so the same. Immediate 7 bits, RS2, RS1, Func3, then immediate. So I think it's the same. Yeah, it's the same. It's just the identifier's width, which doesn't really matter. That's fine. It's not a big deal. So yeah, it'll be the same. So no more implementation there. We're just changing the value, so it's gonna be under stores, and it'll be a case here. Store word and risc-v. FSW. Yeah. And then FSW here. Alright, so that's good. That's good. And now in here is where we need to actually change it. So let's take this value here. Change it to FSW, change it to stores. Okay, no, it's not stores, it's FSW. Okay. Alright, so next step instruction, FSW, and in this case, there's no destination register, so this needs to be RS2. And reflect that in the function. We can actually just go reference our functions up here for that. Should be. Oh, where are they? What the hell? Oh, okay, they're up here. My bad. Alright, so yeah. RS1, RS2, store immediate. Okay, the immediate changed, right? So we need to reference the logic from earlier. Go preview in 3 minutes, or okay. Yeah, we're looking up here. So essentially why I'm doing that is because the immediate changes, the branching is now 11 to 5 bits, 11 comma colon 5, not comma, colon 5, so that takes 7 bits, and then colon 4 colon 0, which takes in these bits, which is what we already implemented the logic for here, 11 5 and 4 0, which does the accurate shift, so we don't need to change anything. This is pretty good. It's done, just waiting for photos to load. Alright man, alright, let me know when you sent it. I'll check it. I'll give some criticism too if I have any constructive criticism, of course. Alright, let's go back down here. Okay, so okay. Get store immediate. A floating point unit is just like for these to decode. It's if it's very similar, it might actually be easy to get it done. I'm not gonna lie. I think the interpreter will take some time though. Might take 2 or 3 streams depending on how long. But so far it's going good. Next is fadd and fmul. Okay, so let's look at these two. So fadd s and fmul s perform single precision floating point addition and multiplication respectively between rs1 and rs2. Okay, and what's the difference here? And fsub performs a single point precision floating point subtraction of rs1 from rs2 from rs1. Okay, so these two will change, but these two can be lumped in together. Pretty sure. Let's see. What explicitly changes? So we have funct 5 now, so it's a completely different paradigm shift. We probably need to change some stuff here. First, before we go on, let's actually test this actually. So let me go into my Gemini here. Let's grab the 32-bit binary. Actually, let's test it first. Right, it works. So this is floating point load word. Floating point load word. F1. Take the value offset by 12 in X4 register, which is what we got. And then we can also try the float store word 1 too, just to make sure. Unknown. Okay, so something went wrong here. Let's check what went wrong. Oh, I forgot. I totally forgot. Sorry, I need to do this part first, always, or I'm gonna forget. So let's just quit out this first. Okay, so I know what went wrong. Opcode is 7 plus 32, 40. So it's gonna be 0x40, sorry, not 0x7, 0x40, and the func3 will be 2 still, so that's fine. Okay, now it should work. No, still not working. Something went wrong. Let's see what's going wrong. Okay, so that should be 2. I mean, that value should be, I'm pretty sure the value should be 40, right? Oh wait, no, yeah, I'm such an idiot, dude. I was doing binary to decimal. Binary to decimal is fine up until 9, but then you start adding letters, so it's fine for the other one, but it's not fine for this. So I need to actually like get the hex. Yeah, sorry, that's why. 0 1 0 0 1 1 1. Yeah, it's 27 in hex. I keep forgetting hex is a bit different. I've totally forgot. That's my bad. So our value is 0x27. Now if we actually load in this value, should work. Yeah, there we go. Alright. Okay, good little debug there. Alright, so enter. Yeah. Alright. Looks to be good. Let's quit out And let's start implementing the logic now. So let's actually look here. So for f_add.s, okay, Gemini got it wrong. Gemini actually got it a bit wrong, I'm not gonna lie. Let's see. Let's see if it corrects, or let's see if what goes wrong. Yeah, so I think it's gonna be a bit different here. Alright, so okay. Properly and tested. Okay, not yet. Yeah, not yet. Or, I mean, I guess we could, right? Start off, or should we just do all the you can hear that well or something? The water. Yeah, my mic is pretty loud sometimes. Alright, so I mean, I guess we could do the interpreter as well. Like, it might be good to like do simultaneously so we can just get it all done. So okay, so the interpreter now, I guess we can start. So in our core, the array of registers for integers does not work anymore. It needs to be float now. So yeah, so we can try implementing a std array, but how do we do that? Oh, it's just float. Okay, float 32. Just call it float 32. The photos are in? Alright, I'll check it. I'll check it right now. One sec, let me just go to Discord properly. Make sure I don't leak anything. Once I'm in, I'll show my screen back. Alright, man. Alright. Yeah, I'll take a look at what you sent. Alright, so actually, yeah, not too bad. Kind of like a retro look. I guess just like fixing some of these little corners. It looks like the buttons kind of overflow, like they're not even. I guess that's the only problem. But everything else looks really nice. I like this kind of like a retro theme, kind of. I like it. Yeah, just like it looks nice. Just like moving some of these, like moving this part here a little bit to the right to like not look like it's going into it, I guess. Oh, that's the old stuff. Oh, that's from yesterday. Sorry. Oh, this is new. Okay, nice. Looks pretty good. Not gonna lie, I do prefer the green for some reason, but that might just be me though. This also looks really nice. The gray might look better for most people, probably. Yeah, I think, yeah, not bad, yeah. Looking pretty good for doing it in one day. I like it. Yeah, that's some pretty good stuff, bro. All right. Well, I'll just keep these Discord open. Lucky once I get more viewers, I'll make it on Discord myself. All right. So okay. So this will be for floating point registers now, and let's reference what they need read and write functions very similar to read, reg, and write, reg. One difference though, floating point registers have the same x0 hardwiring rule as integer registers. Think about what f0 should be in risc-v. Okay, let's try and think about that. There'll be a cave? Nice, man. I'd like to see that once you're done with that. Wait, mark these as red. Alright. Okay. Floating. Okay, let's actually floating point f instructions risc-v. Register state adds 32 floating point registers f0 to f31, each 32 bits wide. Okay. And floating point control and status register FCSR, which contains the operating mode and exception status of the floating point unit. This additional state is shown in the risc-v. Okay, let's take a look. Oh wait, that's just moving down here. Okay, wait, let me. I see. Okay. Or a moon cave? Nice, nice. Okay, wait, so are there 32 registers or are there more? It seems like it's a bit different here. 31 is there, but we have f length, which is the length of the value, length of the register. FCSR, control and status register. Okay, that's interesting. Is a 32-bit read/write register that selects the dynamic rounding mode for floating point arithmetic operations and holds true to exception flags. Okay, interesting. So that's actually very interesting. Okay, let's take a look. Actually, I want to see. I'll take a look at this manual first, though. Quite interesting. Okay. So, okay, let's just continue reading a bit more about this stuff. Just to get a solidified understanding of what's actually going on here. NAND generation and propagation. The result of floating point operation is NAND. It is canonical NAND. Okay. Yes, I get that. Subnormal arithmetic. Single precision load and store instructions. Yeah, I mean, okay, so we understand this part. Don't modify the bits being transferred, in particular the payload of non-canonical NANDs are preserved. Okay. I don't think it matters too much for those ones. But let's see. I just want to go through this and look through. Do we have like a CSR one? Not those. Okay, that's a lot. Okay. So I guess there's not, but for single precision, it's okay. The layout of bits is the same for like literally all of these. So the two easiest ones were these ones. They stayed the same. We had to implement new stuff for this part, but all these are very, very similar. Well, some of them change here. You have an RS3. Okay. And then, yeah, okay, so that makes sense there. So for register state, so how do we actually... Let's actually kind of figure this out. Exit register and integer registers are hardwired to 0 cannot be modified. Floating point registers like F0 can hold floating point values and are not hardwired to a specific value. Design allows room flexibility in using floating point registers compared to integer registers. Okay, we can actually take a look here, actually. Yeah, it's actually better to look at this manual. Probably. We just need to kind of understand it. Okay, wait, this one's not for floating point. This is for floating point. Okay, register state. I see, okay, I think I kind of understand. So, we have 32 registers in itself, but then we have one register that occupies another 32 bits, separate from those 32 that we have. Essentially, that's what I'm understanding from this. We can actually just try and understand it better. Okay. Alright, okay. Let's give Claude what we have here so far, what I learned about these. F0 is a general purpose floating point register, no hard wiring. Okay, wait. So compared to our integer version, okay, so let's put it underneath here. So let's leave a couple more spaces between these. There's three spaces, okay. Yeah, so we have the array for 32, and implement these functions here. So well, the number is going to be int, so that's fine. The register number, but the value itself is going to be a float, so it's going to be a float value itself. So that right fridge. Let's do that. Right, we need to put in our header 5. No, it's already in our header 5, my bad. So this should be fine. And then actually implement it properly in this interpreter. Or I guess we can keep it up with the other right one, so it'll be easier to sustain, probably. Probably better up here, yeah. So we have that. And we're probably just gonna write our... It's literally just gonna be the value itself, because we don't really need it to we don't need the 0 check since x0 is not hardwired to 0, so that's fine. So floating register, okay, and then we can do the right one, the read one too, which will essentially just be the same, and I'm gonna put it here as well. It won't be unsigned int, there will be float. Reading the register, fridge, and just the register number is fine for that. And this will be for the array for yeah. So but we don't want that implementation here. We just want the forward declaration. So this will just be like that. This will just be like that, and then we'll go back here and change that in here. Wait. Sorry. Changing the wrong things. Or no, that was right, sorry. Redo that. Top one will be the read register for integers, and this will be the float one, so we need to change it here. Float and or read average, and that should be good, which is kind of what, yeah. I think we implement the same. Okay, so I guess now for the type putting question on float load word loads 4 bytes from memory, it gets an unsigned integer 32. You need to store those exact bits as a float in the FP register file. Can't just cast float, okay. Did bit cast, but there's another one called memcpy. I probably want to look into that real quick. Memcpy C++. Just look at CP reference for a second. Spy, okay. Pointer to memory location. Copy to pointer. Copy from number of bytes to copy. Interpreting. Sorry. Okay, let's take a look. So how do they actually do it here? Okay, so the address of the float that the pointer is pointing to, address of the unsigned integer value, and the size of float. That looks to be the right parameters here. So if we're reinterpreting here like this, given, let's move this over here so I can actually reference faster. Okay, so I'll be done with the stream after this part. It's just gonna be a short stream today, and we'll carry on tomorrow. Okay, so. Alright, so. So this will be our value, right? Float f. No, we can't do that. So we just instantiate float f here. We're referencing the address of that f, and what would be this unsigned int value that we're talking about here? What is that value that we did? Okay, so wait. Let's go back here for a second. I need to look at these again. So, okay. Alright, so we have our halted, what we want to execute. Reading and writing, okay. We have our memory from earlier that we did, but okay, so what's going on here with the floating point? No, I know that's address of, but what is that actual, like, what is the 32 value that we have? I don't remember instantiating. Case instruction. Oh, he's actually implementing it now in like the actual thing. Okay. So we're not in our interpret anymore. In our header file. Okay. All right. Let's try and implement. We can. So if you have a case for f.w, okay, let's actually like take a look properly. Where is that? Okay, here. Hey, what's up, user? BL4. What's up, man? Alright, okay, so for W, so I need like an actual like way to see what we're actually. Well, it would just be adding these two, not adding, loading them. So let's reference our thing up here. So we would need to implement the value, like a function for reading these words, right? But I guess it would be the same, essentially. The actual like memory instruction itself would be fine. It's just that the value itself needs to be float, which that's what we're doing with the casting, like the reinterpret cast. Okay, I'm just gonna copy this just to have a reference. Let's do it with load word. It's much more closer to what we're trying to implement here. And let's go back down. Okay. Should the moon and the cave be blue or red? For your aesthetic, maybe blue, not gonna lie. But usually red moons are more cool. Yeah, probably do red. Probably do red. Okay. So we are loading from, yes, so we're doing that and storing that in destination register, so that checks out. But here's the thing, that changes a little bit. Right, freg, which will take in integer number and the float value, which will be our memory, since we need to actually change it though here. Okay. How do we change? Okay, so what exactly are we changing? Yeah, that thing. Yeah, I remember now. But this would be in the case of what though? Like, is there a case for it? A special case, or we're just doing it? We're just doing it, it seems. Okay. So down here, we need to actually change it. So after the memory is written, float f. Let's just zero initialize. And that's what we actually do. Std mem cpi. We'll take the address of the float. The address of our memory. I assume it would be memory. Taking the value of memory, the address value of memory, and size of our float. So size of this lowercase, sorry. Size of our actual f value here. And I guess store that in a variable, I guess, right? Or no, we don't need that. Pi. Okay, I I guess I still don't really understand what MCPy does. I don't know, CPU reference, I don't really understand CPU reference that much, to be honest. I need a much more simple thing to understand. Certain library function that is used to copy the specified number of bytes from one memory location to another memory location, regardless of the type of data stored, is optimized for copying memory chunks in an efficient manner and copies memory in a byte by byte format. Okay, yeah, that makes sense. Okay, it makes sense now. So you have char variable, two char variables, address of 1, address of 2, size of B, A. I see. Copying the value of the A into B. So now B mimics the A in the case of ours. So we have, in the case of ours, we have the F that we're initializing. So we have the memory, also the memory here, having F, address of F, address of memory, size of F, and we're copying the memory from this into F so it can properly cast it to the right type without needing like casts and all the other ones that might cause errors. Copy the value, so we're copying the value. Okay, that makes sense. Now let's write the case for the other one too. FSW. Okay. Just leaving this comment for the algorithm. I appreciate you, coder Tassin. I appreciate you, man. Alright, okay, so we have float store word now. Okay, let's just reference our store word. Let's just grab it. It should be very, very similar. We just have to do the cast properly. Okay, so for storing the word, we take in the address and a separate value. So let's actually take a look. Yeah, taking in the immediate. We're taking the rs2 register and storing that value into this offset now. So the offset of immediate 12 for rs1 will now store this value instead. So, okay. So this is the one for the integer version, so let's see. So we have that and that, so essentially this is fine to keep the same there. But the thing that changes will be, okay, so essentially the float. Oops, that always happens to me. Did memcpy address of the float variable, and it wouldn't be the address, it would be the actual value, so we have to do the value, address of the value itself, and the size of f. So copying the value of this over to this with the proper size constraints. And this will be f now. So that should work. That should work fine. Yeah, so we have the float load word 1 and the float store word 1. Reading the register plus the immediate, the value. This should inherently not need any cast or anything, so I think that's fine. But this one we just need to get the value store. So I think we have it right. We just need to not that one. Here. Let's do a quick test, not gonna lie. Let's actually see if it works. So, starting with this one, this value should now be in F1. Let's do it. Let's give it a try. So here, it's done. Let's analyze what happened. Looks like it didn't actually copy over correctly. Our register states didn't change it up. Oh, yeah, that's my bad. Hold up. We need to actually implement it here. We're using different registers. Okay, if choice equals 2, okay, we need to actually change it here. Okay. So now it needs to actually distinguish if it's a I mean, it should be. Should be fine here, like this. So the memory, we're instantiating these two, true, binary string, binary, address and value. That's where, okay. This might be a bit of a problem here, like this, but I'm not really sure how to actually address this issue, to be honest. Yeah, I'm not really sure. Let's see. Yeah, I'm not gonna lie, I'm not exactly sure how to address this issue here. I can ask Claude though. These cases here. These two cases. Sorry. Okay, let's go here. Okay, so for these two cases, right, that we wrote, but in our main function, the register states didn't update. So I believe we need to implement something here. Start. Something's wrong. You're reading from it's a register file with. Oh, did I not change it? Oh, I forgot to change it. That's not bad. It'd be freg for that one, yeah. That's my bad for that one. Yeah, okay, so I changed that. What else? Okay, we had the address. Blood Moon Cave. I have to add a little bit more decorations and DMs, or I'll check it out in a second. Just need to figure this out quick. Okay, I see. So we don't need that value to be an integer. We don't need to store a separate float. We can just make this like that itself. So we have the float f itself, but it's a reverse MCPy, okay. Right, yeah. Hey, what's up, Sticks? How you doing? Just over here? Yeah, I'll remember you. I'll remember you. Loki tough, nice, bro. Thank you, thank you. Right, okay. Right, okay, so for this one we had a reg, so we passed in the float because freg actually passes in the float value. That's my bad. Yeah, that's my bad. I completely missed out because right word is takes an integer, I'm pretty sure. Yeah, an address, memory address, and a value, so we can't actually pass in a float, so I messed that up. So we actually need to instantiate another like value here and just call it like value, and this is what will be in the size of x. So it will be value, size of value, and these can be swapped. And let's do value. I don't know anything about C++, but I know Python. How much time it will take me to learn C++? It'll take you a bit, but like I'm doing this stuff 1 month and 1 month and a half in C++. So yeah, this is not just C++. This is also a computer architecture from this book. Let me show the book cover from this book. I just wanted to read this, so I'm reading that and also building on top of that with C++. So yeah, and then building a project. So just understand the basic fundamentals of C++ and just build on that. If you already know Python, like, you know a decent bit of stuff like object-oriented programming and stuff, it's gonna be a bit hard to like move the syntax knowledge over, but you'll get there. Okay, okay, this should be right now, I think. So we're taking this value here. Yeah, so essentially passing in the address float into the value, we're passing it back to an integer, and then writing the address of that. So it should be fine with that. Okay, let's cover issue 2 now. Let's cover issue 2 that we didn't have. Floating point register dump missing in main. Your register dump only prints integer registers. You need to also print floating point register to see if they're updated. Add after the integer dump. Oh, yeah. Okay, that's literally it. I thought it was going to be a much bigger issue. Okay, that actually makes sense. It's literally just going to be... I'll just copy this. It's the same. So for 32 registers, we have X, and then it'll literally just be that. Okay, I didn't know that solution was so simple. Oh, but I guess instead of X, since the registers aren't X anymore, it's F. Yeah, okay, that's one more change. And everything else is essentially the same. Yo, bro, thanks. I've subscribed to you. See you again. I appreciate it, man. Hope to see you again. Okay. Alright, let's actually test. We can test now. Let's test it out. Okay, so in our binary instruction, let's take the floating word. Oh. And let's type done. And no, it did not. Okay, so something still is wrong. Something is still wrong, but I don't exactly know what. But we can check though. Because this is supposed to store it in F1, but F1 doesn't have any change. It's still 0. Yeah, okay, so let's take a look. Could it be that Gemini gave me the wrong type or something? Okay, I didn't even copy it. Oh my god. I didn't even copy it right. Alright, let's see. It has to be some really dumb mistake that I'm not looking at as to why it's not working. FSW, FOW, read register, right? Everything looks fine, but are we writing to the right? Like, okay, wait, let me look at the right word. Where is the right word? No, it should be good. It should be able to. It has to be something like that. That's okay, that's right. I'm really not sure though. I'm not sure what's the problem. Main choice 2 should be fine. Okay, let's give Claude the query to understand what's going on properly. And also Claude like the actual instruction that I gave, so it can catch anything if anything's wrong. I use that primary and register. Is that FOW loads from memory address x4 plus 12. We test this instead of x4 or put any float value at that memory location, so it's loading from which contains instruction bytes on a float. Testing your main before cord on for testing. Okay. I had like that thought kind of ran through my mind, but I wasn't actually sure if that's right. So, like, I thought that the values weren't actually in, but I guess we can. Yeah, I guess we can just have that little test. So this will be before core out run in here. Going for F. Okay, I think I kind of get it. Alaska, Gemini. Give me these 2 bits. Alright, let's give it a test. So if you have that, okay, so the first one, loading the value 100 into x4. Oh, where am I going, bro? Right, yeah, loading the value of that, and we also need to now load in that value from 0x4 into float.1. Say done and see if it changed. There we go. So it looks like the logic worked. I just didn't add a test case for that, like the proper way. I see. And okay, wait, so okay. Let me just try and understand this more. Okay. F1, X4. What happens if we don't have this at all? Like, comment it out and do the same thing here. So here, if we just do these values, but like don't change anything. Just like this. So in that case, F0 does not change. F1 does not change. Okay, it kind of makes sense to me now. That's doing okay. Okay, so that works. The test worked. So just want to check it one more time, just in case. Not gonna lie. Go back. Sorry, other way around. Other way around. We can't have this here. We need to do this first. Okay. This and this. Done. Yeah, 3.14. I actually want to see what would happen if we did the other way around, actually. Like, so if we did this first, then did this. Theoretically, it should do nothing to F1, but actually have the value of X4, F1. Oh, wait, what? Interesting. But then this value would be 100, yeah. That's very interesting. Wait, why does it do that? So within this register at that offset, it has no value stored, but we initialize that anyway, so I wonder why it actually does it. I'm not gonna lie. Oh, we can ask Glenda. Okay, we're expecting. So first, let's do this query here. So I tested and it works, but I played around with it a little bit and saw input then just for curiosity and it put this is just for my curiosity to see. It's just exactly what you expect once you think it through. Yeah, still zero initialized. Yeah, okay, I got that part, but why does it change to that really low number? Address 0 contains your first instructions bytes. Encoded as 32-bit integer. When its bytes get reinterpreted as a float via memcpy, you get a garbage float value like that. Okay, so essentially it reads that and sees if if you do that first, it reads that and sees that it's just garbage and then outputs that. Okay. It's not a bug, it's your emulator correctly loading whatever bytes happen to be at address 0 and reinterpreting them as a float. Okay. Yeah, that makes sense to me. I assumed it was some type of like garbage value or something. Just wanted to make sure. Okay, that's fine, but now I want to actually generalize the value. So if I just do like that. Okay, get a value from the user. I was just about to ask. Yeah, I guess that would be easier, but I think I'm gonna wrap it up for today. And yeah.